Have you ever wondered why copper wires are used in almost every electrical device around us? Or why water doesn't conduct electricity unless we add salt to it? Well, both these everyday facts are rooted in the chemistry of electrical conductance, and that's what we'll dive into today. Let's begin with the basics. Electrical resistance is a measure of how much a material resists the flow of electric current. We denote it by the capital letter R, and it is measured in ohms. Now, resistance increases with the length of the conductor and decreases with its thickness. In formula terms, resistance equals resistivity multiplied by length divided by cross-sectional area. That's open bracket R equals rho times L divided by a close bracket. Here, rho represents the resistivity of the material and its unit is ohm meter. The inverse of resistance is called conductance. We denote it by capital G and it is measured in Siemens, also called ohm inverse. Conductivity, represented by the Greek letter kappa, is the reciprocal of resistivity. It tells us how well a material conducts electricity per unit dimension. Now that we know what resistance and conductance mean, let's talk about the two ways in which substances conduct electricity. First, we have metallic conductance. This happens in metals and is carried entirely by free-flowing electrons. Here, the metal doesn't change its composition. No new substances are formed. Second, we have electrolytic conductance. This occurs in liquids or solutions and is carried out by ions. That means positive and negative ions move through the liquid and chemical changes often occur at the electrodes. This ionic conductance is affected by several factors. It depends on the type of electrolyte, the size and charge of the ions, how easily they move in the solvent, the viscosity of the solvent, and temperature. For example, pure water has very low conductivity, about 3.5 times 10 to the power negative 5 Siemens per meter, because it barely ionizes. But add some table salt, and you'll immediately see a spike in conductivity because of the additional sodium and chloride ions. Now let's discuss how we measure this ionic conductance. We use a device called a conductivity cell. It typically has two platinum electrodes coated with platinum black to enhance surface activity. These electrodes are placed at a known distance apart and have a fixed surface area. The resistance of the solution in this cell is calculated using the same formula. Resistance equals resistivity multiplied by length divided by area. But in practice, it's difficult to measure length and area precisely, so we define something called the cell constant. It is denoted by capital G with an asterisk and equals length divided by area. Its unit is per meter or per centimeter, depending on the measurement system. We usually determine the cell constant by measuring the resistance of a standard solution like potassium chloride, which has a known conductivity at a given temperature. Once the cell constant is known, the conductivity of any other solution can be calculated using the equation conductivity equals cell constant divided by resistance. Let's now move to a more chemically meaningful measure, molar conductivity. Molar conductivity is defined as the conductivity of the solution divided by its molar concentration. In formula terms, molar conductivity equals conductivity divided by concentration. If conductivity is expressed in Siemens per meter and concentration is in moles per cubic meter, then the units of molar conductivity are Siemens meter squared per mole. Alternatively, if conductivity is given in Siemens per centimeter and concentration in moles per liter, then molar conductivity is calculated by multiplying conductivity by 1000 and dividing by molarity, and the unit becomes Siemens centimeter squared per mole. So, molar conductivity gives us the conductance of all ions produced by 1 mole of electrolyte in a given volume. That makes it very useful for comparing the ion-carrying ability of different electrolytes. Here's something fascinating. Conductivity and molar conductivity behave very differently with dilution. As we dilute a solution, the total number of ions per unit volume decreases, so conductivity, which is the conductance per unit volume, also decreases. But molar conductivity behaves the opposite way. As we dilute the solution, the ions move more freely due to reduced interactions, and molar conductivity increases. In fact, at infinite dilution, molar conductivity reaches a maximum constant value called limiting molar conductivity. We denote this by capital lambda with a superscript naught. For strong electrolytes like sodium chloride, a graph of molar conductivity versus square root of concentration gives a straight line. For weak electrolytes like acetic acid, the curve rises steeply with dilution due to greater ionization. Kohlrausch's law gives us a powerful insight into ionic mobility. It states that the limiting molar conductivity of an electrolyte is the sum of the individual contributions of its cation and anion when the electrolyte is infinitely dilute. So, for sodium chloride, the limiting molar conductivity is equal to the limiting conductivity of sodium ion plus that of chloride ion. Numerically, that's 50.1 for sodium plus 76.3 for chloride, which adds up to 126.4 Siemens centimeter squared per mole. This law helps us calculate the limiting molar conductivity for any electrolyte, even for weak ones where direct measurement is difficult. It's also used to determine the degree of dissociation and dissociation constant for weak acids like acetic acid, which is vital for acid-base equilibrium studies. So let's summarize what we've learned today. Electrical conductance is not just about wires and circuits. It is deeply linked to how ions behave in solution. We started with resistance and conductivity, then moved to how electrolytes conduct current through ionic motion. We explored how to measure this conductance using platinum-based conductivity cells and calculate molar conductivity, which is a better indicator of ion mobility. We saw that while conductivity drops on dilution, molar conductivity increases, especially for weak electrolytes. And finally, we looked at Kohlrausch's law, which allows us to break down limiting molar conductivity into the contributions of individual ions. This entire concept helps chemists in fields ranging from analytical titrations to battery design to industrial purification. I hope this session helped you understand how conductance connects electricity to the world of chemistry, from the movement of ions in your electrolyte drink to the functioning of smart sensors in laboratories. Catch you in the next class, where we'll continue unlocking more invisible forces of chemistry in action.